Hello everyone, welcome back. Today I'm going to be going through one of the 2022 prelim papers for H2 Maths that I've received, which is Daman High. When I had a look at this paper, I tried it for the first time, I thought some of the questions are pretty interesting, so let's give it a shot. Now, I've actually done this paper beforehand so that I can speed up the recordings and make less mistakes as I record, which will minimize the amount of editing I need to do later on. So, let's just go through the questions. It'll be the same procedure as we always do. So for the first question, it's an inequalities question. So one part A. Show that negative x squared plus 6x minus 14 is always negative. Well, this is just completing the square, right? So I can actually complete the square. This will be minus x minus 3 squared, which is negative x squared plus 6x minus 9. So you subtract another 5 to get the completed square form. Alright, since x minus 3 squared is greater than or equals to 0, negative x minus 3 squared minus 5 has to be less than or equals to negative 5, which is definitely less than 0. Alright, cool. Alright, so how is that relevant to the later part? We'll see. For part 1b, solve this inequality without using the calculator. We have x minus 5 divided by x minus 2 greater than or equals to 3 over 4 minus x. Okay? So we're going to combine the denominators as per usual, which gives us x minus 5 times 4 minus x minus 3 times x minus 2 divided by x minus 2 4 minus x, and this is greater than or equals to 0. We'll simplify this. If you simplify this, you'll get a negative x squared from here. Then what is the coefficient of x? This is a 5x, 9x, then minus 3, so plus 6x. And what is the constant term? Minus 20 plus 6 minus 14. Okay, then the bottom is still x minus 2, and I'll actually change this to x minus 4, and I'll rewrite this as less than or equals to 0. Okay, then you'll notice actually this is the exact same as what we proved in part 1a. Okay, so this is from part 1a. Negative x squared plus 6x minus 14 is less than 0 for all real numbers of x. So it comes down to solving x minus 2, x minus 4, and because denominator is excluding, you cannot have it equals to 0. We will solve this to be, we have less than already, we want this to overall be less than or equals to, so this is more than 0. Alright, and you can proceed to solve this the usual way. X is less than 2 or x is greater than 4. Cool. Alright. Part 1c, find the solution of the inequality ln x plus 5 divided by ln x plus 2 greater than or equals to 3 over 4 plus ln x. Can you see the connection between the two parts? If you think about it, you actually need to use part 1b to help you. So from part 1b, replace x by minus ln x. Alright? And just so that you can verify that this will be the case, if I had x minus 5 and I change that to minus ln x, that's minus ln x plus 5, and minus ln x, minus ln x minus 5, minus ln x minus 2. The negatives will cancel out on top and bottom to give me the one on the left hand side, and you can also check the right hand side. So we have to solve minus ln x less than 2 or x minus ln x is greater than 4. Okay, which you can change to ln x is less than negative 4 or ln x is greater than negative 2. Alright, so we can of course raise both sides to the power of e, but remember ln has to be, the input of a ln must be positive. So you actually have to put 0 here, 0 less than x less than e to the power of negative 4, or uh, ln x has to be greater than e to the power of negative 2. Alright? And yeah, that should be the answer. We now go on to question 2, which is a transformation sketch. So we have this curve. You can see we have like these parts and some features. Well, you can see for yourself. So reciprocal graph. How to sketch reciprocal graph? Now let's just quickly discuss what happens to each of the features. When you take a reciprocal graph, the horizontal asymptote y equals to half. When you take the reciprocal, it becomes a y equals to 2 asymptote. This half intercept here will become an asymptote. This minus 2 asymptote will become an intercept. And this oblique asymptote disappears. Oblique asymptotes become y equals to 0 asymptotes. So your x-axis will actually be an asymptote of this curve. Okay. So let's see what happens. Okay, so this part is actually decreasing, and this minimum will become a maximum. This minimum becomes a maximum. So this is a decreasing function. So this is going off to infinity. So you start tending towards 0, but then it will actually increase until you reach the maximum point. Actually, it might be easier to draw in the asymptotes first. So let's do that. This is the y equals to 2 asymptote. Okay. And 2 will be a horizontal intercept later. Okay. Negative 2. Okay. So we start from here and we go to negative 5 over 2, which is, and 4 over 3. 4 over 3 is somewhere here, right? Okay. So our point will pass through somewhere there. So you try to draw a curve that approaches the asymptote but has a maximum point somewhere here. Okay. Then we're going to draw it down and it's going to come down here. Now take note that actually this is also going to be a turning point because both sides are positive, so this is going to go back straight up. Okay. And this is going to hit the minimum point here, which will become a maximum point. And because this the y-axis is actually also a vertical asymptote, so it will actually pass through the origin also. However, half will become an asymptote. Okay. So let's see what happens. So we come back down, quickly come here. Oops, how do I draw this? It will turn here and it will become, this will become the turning point. And it will come back up. And it will hit this turning point and it will come back down again. Okay. It will come back down through here. It will pass through origin and it will approach this asymptote. How to draw? Okay. From here, continue on. Alright, something like that. Okay. So this is the origin. This is the point that corresponds to B, so I will label this B prime. And this is still negative 1, 1. This is the point 2, 0. Negative 2, 0 rather. This point here corresponds to A, so A prime negative 5 over 2. and 4 over 3. Right, and the y equals to 0 asymptote. So this becomes negative, and it's going to become positive, so it's actually going to come up from this side. And it's going to, C is going to lie below this asymptote. It's actually going to be at 1 and 1.5. So that's somewhere here. Okay, and then it will tend towards the asymptote. So coming down here, and then it will turn back up. Okay, so your turning point is somewhere here. C prime, 1.5. Okay, and yeah, that will be the sketch of y equals to 1 over f of x. Okay, did I miss anything? No, I think we're good. Okay, so that will be the reciprocal graph. We also have to sketch the derivative graph for part B. Okay. Yeah, okay. 2B. Okay, so any horizontal asymptote will become the x-axis asymptote, which is still y equals to 0. And we have an oblique asymptote with gradient -1. So when you take the derivative of this, you will actually get y equals to -1 asymptote. The vertical asymptotes will stay, and any place that becomes a turning point is now going to be a intercept. So let us draw the line y equals to -1, because this will be the horizontal asymptote. Okay. So what happens? So we see that actually it is approaching -1, but the gradient is increasing. This function is increasing here, and the gradient eventually becomes positive at -5 over 2. So that's somewhere here. And then it will become an asymptote at 2. So actually, let me move this a bit to the left, because this part is decreasing, so it will be negative later. Okay, so it's gonna start here and it's gonna go up, right, and then it's quickly going to rise after this part. If I can draw this. Maybe I need a bit more room for this. Okay. All right. There you go. Okay. So that's that. This is -5 over 2. This is b prime. Sorry, this is a prime. -5 over 2 and 0. Okay. And this part is going to increase. It's actually going to intercept here at b prime, -1 and 0. And it's going to continue increasing. And the y-axis is actually still an asymptote. So, and the function continues to increase over here. So I can write this over here. X equals to 0 is an asymptote. Okay. So this function is going to increase from this horizontal asymptote. Okay. It's going to cut at -1, because that's when it starts to become an increasing function, and then it will approach the y-axis as a vertical asymptote. So something like that. Okay, so this is b prime, -1 and 0. Alright, it's going to come down from here and it's going to hit 1, and then it's going to decrease from that point. And there will be a turning point somewhere. The gradient of the curve looks like it is going to decrease at a rate steeper than the -1. So personally, I'm going to draw the curve going underneath, and then it will actually come back up and approach. Yeah. So what I mean by that is it's going to decrease until here. It's going to actually cut this asymptote because I feel like the gradient at that point of the curve is less than -1. Although, personally speaking, I don't think, and by the way, this is also what the Dunman solution gives, but personally speaking, I don't think they'll be too strict with it, because yeah, it's quite hard. You can't like discern exactly what the gradient is as well. So if you draw it slightly above if you end up drawing this curve part above the asymptote, I think they will still give it to you. Okay, and the y equals to 0, of course, as a horizontal asymptote. And this is the point C prime, which is 1 and 0. Okay, is that everything? I believe that is everything. Okay, cool. This is the graph of y equals to the derivative of f of x. Okay, that's all. Okay. Question 3 is integration. We're going to find the derivative of e power sine square 2x. All right, be careful with the numbers in this question. All right. Now, when we take the derivative of e to the power of a function, we find the derivative of that function multiplied by this thing. The derivative of sine square 2x is you bring down the power 2 sine 2x, and then you find the derivative of sine 2x, which is 2 cosine 2x. So this is 4 sine 2x cosine 2x e power sine square 2x. Okay? And this can actually be simplified because of the double angle identity for sine. So this becomes 2 sine 4x e to the power of sine square 2x. Okay, that's that. 3b, we're going to find this integral. It looks scary at first, but it's only 2 marks, so there has to be some sort of trick to it. So we're going to find the integral of e sine square 2x sine 4x divided by the square root of 1 plus e to the power of sine square 2x dx. Okay? This looks scary, but believe me, it really isn't that scary. Because let's say that this is function f. We ignore the square root. We take the derivative, we're going to get this times 2. So this is actually half times the integral of f prime x, f of x to the negative half power dx, where f of x is 1 plus e sine squared 2x. So it's an f prime x, f x power n kind of integral. Okay, which is just f of x to the power of half divided by half, which cancels out with the half on the outside. So you're just going to get square root of you're just going to get f of x itself, which is 1 plus e sine square 2x plus c, because the halves cancel out. All right. Now for 3 part C. Find the exact value of this definite integral. We're going to integrate from 0 to pi over 4 of e sine squared 2x sine 4x cosine squared 2x dx. Okay, so what is your approach for this question? Well, I know how to integrate e sine squared 2x times sine 4x. So I'm actually going to make use of integration by parts. So let me call this my, okay, I know how to, let me just highlight this and make a note. We know how to integrate. Okay, so let's call this our v prime and we'll call this to be our u. And then we'll apply integration by parts. So if I integrate this, I'll get half e sine squared 2x cosine squared 2x. Alright, and now we're going to minus u prime v, right? So if I take the derivative, this is minus 4 sine 2x cosine 2x. Alright, and multiply this by half e, okay, I'm going to need a bit more space. Half e sine square 2x dx, and this is a definite integral 0 to pi over 4. Okay, and I can evaluate the left part first. So this is, if I put pi over 4, this is going to give me e. Actually, no. If I put in pi over 4, this is just going to be 0. And if I put 0, this is going to be just half. Negative half, right? So it's negative half. And I'm going to get this integral. This is actually, if you notice, this actually simplifies to sine 4x as well. So I can actually integrate this because sine 4x times e power, same thing. So I can actually integrate this. So this is negative half plus, and the half will cancel out here. So this just becomes a simple integral of e sine squared 2x sine 4x dx. And this is going from 0 to pi over 4. And yeah, I just need to literally use the thing I've done before, which is, this is going to be e sine squared 2x, right? Going from 0 to pi over 4. Okay, and if I put in pi over 4, this is half e, and if I put in 0, this is 1. So this is going to be half e minus 1. All right, yeah. Pretty cool. Okay, question 4 is a pretty interesting question. It's a complex numbers question, although I will say that what they have provided is I suppose it's a possible method, but actually I didn't use this at all. So what they have given here is the cosine theta plus I sine theta power n equals to cosine n theta plus I sine n theta. This identity holds for any positive integer n. In fact, it holds for negative integers as well. This is called the De Moivre's theorem. Okay, it's useful for like this is used together with binomial theorem to derive the Chebyshev polynomials, which are trigo polynomials. It's very cool. Although the Chebyshev polynomials are traditionally defined by the recurrence relations, this is an alternative way to derive them. Yeah, but I'm actually not going to use this result because they did not specify that you have to use the result. You may, it's not you must. All right. So personally, I'm going to present a solution which does not use this method, or yeah, or it might use this method implicitly. I'm not sure. I'm not sure if it counts as implicitly using this method. But what I'm going to demonstrate is a bit different. Okay. So we are given the question of finding the exact possible values of theta where negative pi over 2 to pi over 2 to satisfy the equation cosine theta plus I sine theta to third power plus cosine theta plus I sine theta to the fifth power. This is equals to negative half minus root 3 over 2i. Alright? Now, whenever you're dealing with polar forms, it's always good to make everything into the same form. And personally, I like the exponential form the best. So I can actually write this as e to the power of 3i theta plus e to the power of 5i theta. And this equals to, we're going to convert this into a polar form complex number. If you draw your Argand diagram, you will see that the angle is negative 2 pi over 3, and the modulus of this is 1. So this is actually e to the negative 2i pi over 3. Okay? I should not put this equal here actually. This is implies, not an equal. Okay? So what I'm actually going to do now is I'm going to pull out an e to the 4i theta. Alright, I'm going to factor out an e to the power of 4i theta, and you'll see why in a minute. So this is e to the negative I theta plus e to the I theta. So it's the sum of a complex number and the conjugate. So this is still e to the negative 2i pi over 3. Okay. Now this is actually a real number. This is 2 cosine theta, in fact. 2 cosine theta e to the 4i theta equals to e to the negative 2i pi over 3. Alright, and now I'm going to bring everything, all the e terms to one side, and I'm going to bring this to the other side. So we'll have e to the I 4 theta minus 2 pi over 3. Plus actually. Yeah, plus. And this is equals to half secant theta. Alright? And we know that this right hand side is a real number, so the left hand side is a real number. So we will say need e to the I 4 theta plus 2 pi over 3 to be a real number. So the imaginary part is 0. And how can we get a real number out of this? We need if you draw your Argand diagram, you know the argument must be 0 or pi, right? So actually it needs to be a multiple of pi. So 4 theta plus 2 pi over 3 is a multiple of pi. And furthermore, we are given that negative pi over 2 is less than or equals to theta, less than or equals to positive pi over 2. So we will write down the possible values of theta. So how do we get this? What's the smallest possible value of theta? Well, this plus 2 pi over 3 allows me to bring this to negative 5 pi over 6. No. When you add this, is 4. It's negative 7 pi over 6, is it? I'm a bit confused. Let me write this as 4 pi over 6, and this is 3 pi over 6. Yes, so this is negative 7 pi. Oh no, it's the other way around. This is negative pi over 2 plus 2 pi over 3, so this is negative pi over 6. Is it? Less than or equals to theta plus 2 pi over 3. Less than or equals to pi over 2 plus 2 pi over 3. This is 7 pi over 6. No, I should do the 4 theta first. Negative 2 pi less than or equals to 4 theta less than or equals to 2 pi. Alright, then add the 2 pi over 3. This is negative 4 pi over 3 less than or equals to 4 theta plus 2 pi over 3 less than or equals to 8 pi over 3. Okay, there you go. So now I can write down the possible multiples. The possible multiples will be negative pi, 0 pi, and 2 pi. So I let this be 4 theta plus 2. So this can be negative pi, 0 pi, and 2 pi. So let's write down the possible values of theta. So this is 2 pi over 3. So this is negative 5 pi over 3. So negative 5 pi over 12. I let this be 0. This is negative pi over 6. What else can it be? If I let it be pi, then this will be pi over 12. And finally, if I let this be 2 pi, this will be pi over 3. Is it? Yeah, okay. This is so far what I got so far. Okay, so we're going to now consider, we're just going to sub each of these values in turn and check whether it is true. Check whether the identity is true. So if I sub in negative 5 pi over 12 and for example it is a solution, then what I should expect is to get e negative I pi, which will be negative 1. Okay, so half secant negative 5 pi over 12 is unfortunately not equals to 1, either plus minus 1. It's not equal. Half secant negative pi over 6, this is also not equals to plus minus 1. Half secant pi over 12 is also not equals to plus minus 1. In fact, the only solution is half secant pi over 3. This is equals to positive 1. So therefore, theta equals to pi over 3 is the only solution. Alright, this is the only solution. We did all that work and we found only one solution, but true enough, there's only one solution. Yeah, okay. So pretty interesting. Let's see. I should be able to do, how many questions have I done? I've done 3 questions, right? 4 questions actually. So how many marks did I go through? 7, 6, 7, 6, 26. Okay. I'll do this question and question 6, and then we can stop for today. Or we'll do question 7 also. I'm not sure. Yeah, I'll leave question 7 for another time. Let's do 5 and 6. Okay. 5a. Okay. We have the curve y squared equals to 2 sine x. Sorry, not 2x, just x. Okay. Plus 2xy. This is to find dy dx, of course, we want to do implicit differentiation. So differentiate both sides with respect to x. We're going to get 2y dy dx equals to 2 cosine x plus 2x dy dx plus 2y. Okay, so bring the dy dx terms together. So 2y minus x dy dx equals to 2 cosine x plus 2y. Alright, and all the 2's will actually cancel out. So let me factor out the 2 in fact. So 2 cosine x plus y. And in fact the 2's will cancel out. So dy dx will become cosine x plus y divided by y minus x, which is exactly what we wanted to show. Okay, find the coordinates of the stationary points. Okay, so this is pretty typical. I'll leave you to do the work. Or rather, I will just show the steps and you can calculate the values yourself. I already have the values written down with me. Okay, so we're going to let dy dx be 0, and of course this immediately implies y equals to negative cosine x. But we don't have any numbers, so how are we supposed to get this to be true? Well, we just literally sub the y equals to negative cosine x into the equation of the curve. So what I will get is cosine square x equals to 2 sine x minus 2x cosine x, right? Okay, and we're just supposed to solve for the values for which this is true. Okay, and we're solving this for 0 to 2 pi. Alright, and of course you will realize that you can't really solve this algebraically. You will have to use your GC to help you with this. I've already done this question, so I happen to know that there are two values of x which will satisfy this, and they are 0.87394 and 4.4877, to 5 significant figures. Alright, and we can also find the associated y values. This is negative 64181, 0.64181, and the other y value is 0.22280. Okay, so these are your turning points, and you can find the second derivative. So we have y minus x dy dx equals to cosine x plus y. We'll differentiate again both sides with respect to x. And this gives us y minus x d2y dx squared plus dy dx minus 1 dy dx. This is equals to negative sine x plus dy dx. Okay, and if you want, you can obtain a d2y dx squared. d2y dx squared is equals to, actually no, we don't need to make d2y dx squared the subject, because we're going to let dy dx be 0 anyway. Then we will get y minus x d2y dx squared equals to negative sine x. Okay, so in such a case, d2y dx squared is sine x divided by x minus y. Okay, then you can go ahead and sub in the values. So one of the values was 0.87394. Y equals to negative 0.64181. And this is actually, how do I write this at the bottom? Y equals to negative 0.64181. This is going to be 0.506 3SF, and this is greater than 0, so this is a minimum point. And I can do the same for the other one, d2y dx squared, evaluated when x equals to 4.4877, y is 0.22280. This is negative 0.229. Alright, and this is also 3SF, so this is less than 0. This is a maximum point. Alright, cool. So very typical question this is. Question 6. This is McLaurin's. We're going to let y equals to cosine ln 1 plus x. Okay, now there isn't really any implicit differentiation we can do on this to make it easier at the moment, so let's differentiate this explicitly. So dy dx, when you differentiate cosine, you get the derivative of the inside, then times negative sine. So you get a negative sine ln 1 plus x divide by 1 plus x. Alright? And to make this a bit easier, we're going to actually put the 1 plus x on the side. So 1 plus x times dy dx is negative sine ln 1 plus x. Okay. This is now we can differentiate implicitly. And the left hand side is 1 plus x d2y dx square plus dy dx itself is now going to be negative cosine ln 1 plus x ln 1 plus x divide by 1 plus x, right? And we can multiply throughout. Actually, this is and I should say this is minus y over 1 plus x. We're going to multiply throughout by 1 plus x, so we get 1 plus x squared d2y dx squared plus 1 plus x dy dx, and I'll bring over the y now, so plus y equals to 0. And that's what we wanted to show, right? Okay. So we'll make use of this result and differentiate further. Oh, it's still the same part. Okay. So we're going to differentiate both sides with respect to x, and we're going to do this twice because we want the fourth derivative to get the power 4 term. Okay, when I differentiate this, I'll get 2 1 plus x d2y dx squared plus, I still need to keep this and differentiate. I differentiated this first. Okay, I need to do this 1 plus x squared. D3y dx cubed. And I need to do the same for x dy dx. So this is dy dx plus 1 plus x d2y dx squared plus dy dx. Okay, and this is 0. And I can simplify this. So this is 1 plus x squared d3y dx cubed plus 3 times of 1 plus x d2y dx squared plus 2 dy dx. Is it? Yes. Okay, 2 dy dx is equals to 0. And I will differentiate this one more time. That's the thing about Maclaurin's. Sometimes you're going to do quite a lot of differentiation. Okay, I'm going to now get 1 plus x squared d4y dx power 4. Yes, this is real. Okay, and you'll notice that when I differentiate 1 plus x squared, I'm going to get 2 1 plus x, and when I differentiate this anyway, I'm also going to get another d3y dx cubed, so I might as well combine them together now. So this is going to give me actually 5 times 1 plus x, because 2 plus 3, right? d3y dx cubed. And the same with the d2y dx squared. When I differentiate this, I'm just going to get 3 of that. I differentiate this, I'm going to get d2y dx squared anyway. So add 5 d2y dx squared, and this is 0. Okay. Yeah. All right. And then you can go and find the values. In fact, they're already given to you somewhat. You just need to like work backwards, and that's actually you can work backwards, of course. So if you work backwards, you get y equals to 1. Dy dx is actually 0. d2y dx squared is going to be 1. d3y dx cubed is 3. d4y dx power 4 is negative 5 over, sorry, it's negative 10. Yeah, negative 10. Alright, you can verify this if you want, of course. So if I do that, if I put in y equals to 1 first, for example, or rather dy dx is what was dy dx? Dy dx was this thing. So if I put in 1, if I put in 0 rather, ln 1 is 0, what? And then sine 0 is also 0, so definitely is 0. And I will use the rest of these results. 0, 1. I want this to be negative 1, so d2y dx square is, oh, it's negative 1 actually. I just realized. Sorry about that. This is negative 1. Okay, d3y dx cube, you can sub in. So this is negative 1. Sorry, this is negative 1. This is 3 whatever, and this is 0. So you want this to be sorry, this is what you want, and this is negative 3. So you want this to be positive 3. So you let this be 3. And finally, this is 3, this is 15, and this is 10. So this is negative 10. Alright, there you go. So therefore, you can write y is equals to 1 minus, oh actually you can just quote what they just wrote there. 1 minus half x squared plus 1 half x cubed minus 5 over 12x power 4. Okay. Of course, you can write down the general Maclaurin series, like with the factorials and everything, and simplify from there. By using the result in part A, deduce the Maclaurin series, find sine ln 1 plus x. Okay. So, no, not 3b, 6b. So, if you recall correctly, or dy dx is actually negative, actually no, I'll write it in this form. We shall recall that sine ln 1 plus x was actually equals to negative 1 plus x y, alright? And we can, sorry, dy dx. Yes, okay? So we can actually take the derivative of this series. So this is negative 1 plus x, and then we'll take the derivative of the first two terms. So when the 1 is gone, so differentiate this term, you get negative x. Differentiate x cubed, okay, so you get plus 3 over 2x squared. And you're deducing it up to the power x cubed, so you just need an x cubed term. So that will be minus 5 over 3 x cubed. And that's it. You do not need any more terms from here. So from here you can work out what the terms are. So there's no constant term, but there is an x squared term, negative, and then half. So this is a positive half because of negative outside. So this will be, oh, I forgot there is an x term actually. There is an x term, which is just x itself minus half x squared. Okay, and then the x cubed term is just 3 half minus 5 over 3, and that's 9, wait, 9, negative, alright, negative, but that's a negative on the outside, so this is plus 1 over 6 x cubed. Alright, and then so on and so forth. Just the first 3 terms. Okay, cool. Hence, write down the equation of the curve, tangent to the curve, y equals to sine ln 1 plus x at x equals to 0. Now, for this question, the conceptual thing you need to take note of is that at x equals to 0, the expansion is actually exact. So, we just need we know that when x equals to 0, y is 0 as well. And what is the gradient of the curve at this point? So, dy dx was actually, well, this is the If we take the derivative of this is going to be 1 minus 2x. Well, actually, it's just going to be 1 because every other thing is going to be in terms of x, so it's all going to reduce to 0. You just have the 1 here. So in fact, it's a line passing through the origin with gradient 1, which is the line y equals to x. Okay? Yep. So that will be questions 1 to 6 of the Daman High paper 2022. I'll leave the paper available for download in the description as well as the official solutions from Daman High. Uh, in the future, I will go through the remaining questions for this paper as well as paper 2. So that will be questions 7, 8, 9, and I think there are 11 questions total. Yeah, the real world contexts are quite challenging. So I'm looking forward to showing those. Alright, so until then, that will be all. And take care. I'll see you guys next time.